Have you ever had one of those days? You tell someone you've been working hard all day, but you feel like you've gotten absolutely nothing done? Well, you might be surprised to hear that in the world of physics, you could be totally right. We're about to see how words we use every single day, like work, have these incredibly specific and sometimes pretty mind-bending meanings in science. So let's get into it.
First things first, we've got to talk about the word work. Now, in our daily lives, work just means any kind of effort, right? Mental, physical, you name it. But in science, yeah, it's a whole different ballgame, and that's where all the fun confusion starts.
Okay, look at this. This is where it gets wild. You could be studying for an exam for hours, totally drained. Or picture this. You're pushing a giant boulder with every ounce of your strength. You're sweating, you're straining, or maybe you're just standing still holding a really heavy box over your head. In normal, everyday language, that is definitely hard work. But according to the laws of physics, you've done precisely zero work. Nothing. Nada.
So what is going on here? Is physics just trying to tell us that all our effort is meaningless? No, not at all. There's actually a very clear, very logical reason for this, and we're about to uncover it together.
The whole secret lies in the beautifully simple definition that science uses. See, for work to actually happen, in a scientific sense, two very specific things have to occur, and there are no exceptions.
Here they are, the two golden rules. First, a force, a push or a pull, has to be applied to something. That makes sense. But here's the absolute deal breaker, the second part. That object has to move. It has to be displaced from where it started.
And this explains everything. It's why our earlier examples all added up to zero work. Remember pushing that rock? You applied a force, for sure, but the rock didn't budge. Holding the heavy load? Again, the load didn't move. And studying? Your brain was on fire, but you weren't physically moving an object with a force. And that brings us to the simple, unbreakable rule of physics. No movement, no work, period.
So here it is, all wrapped up in a neat little formula. Work is simply the force you apply multiplied by the distance the object moves. W equals F times S. That's the whole secret. It's not about how tired you feel. It's all about a force causing something to actually change its position.
Okay, so if work requires a force and it requires movement, what gives something the ability to even apply that force to begin with? Well, that's where we need to bring in work's very close relative, energy.
In physics, energy is just the capacity to do work. It's that simple. If you have energy, you have the potential to make stuff move. And hey, notice the unit here, the joule. It's the exact same unit we use for work. That's a huge clue that these two things are basically two sides of the same coin.
This quote right here is the absolute key to understanding everything. Work isn't a thing you have, it's a thing you do. It is the process of transferring energy from one thing to another. So when you push a box across the floor, you are literally transferring energy from your body to the box. Work is the transfer.
So what does this energy actually look like? Well, in the world of motion and mechanics, it basically comes in two main flavors. You've got the energy of things that are actively moving, and then you've got energy that's just stored up, waiting to be let loose.
First up, we've got kinetic energy. This is the easy one to spot. Anytime you see something moving, anything at all, you are literally watching kinetic energy in action. It's the energy of motion.
Just think about it for a second. A speeding car, right? It has a massive amount of energy to do a lot of work, and a lot of damage if it hits something. A fallen coconut, the wind that's strong enough to turn a windmill, an athlete sprinting down the track. All of these have kinetic energy simply because they are moving.
And here's how we actually calculate it. The formula is 1/2 times the object's mass times its velocity squared. Now the really wild part here is the v for velocity. It's squared. That means if you double an object's speed, you don't just double its energy, you actually quadruple it. So speed has this huge outsized impact on kinetic energy.
But what about energy that isn't causing motion right now? Well, that's where our second type comes in, potential energy. This is energy that's all stored up because of an object's position or its physical state. It has the potential to do work.
Look at these examples. A stretched rubber band isn't moving, but you just know that if you let it go, it's going to snap back. That's stored energy. Water held back by a dam, the spring inside a wound-up toy car, an arrow pulled back on a bowstring, all of these are just containers of potential energy, waiting for a trigger to be released.
Now, one of the most common forms you'll see is gravitational potential energy. When you lift a book off the floor, you're doing work against gravity to get it up onto a shelf. That work, that energy you spent, is now stored in the book. And the formula is super simple. It's the mass of the object times the force of gravity times the height you lifted it. The higher it goes, the more energy it stores.
And now we get to it, the most fundamental, most beautiful rule in all of physics. This is the law that governs everything from a falling apple to an exploding star. It is the law of conservation of energy.
This is it. Let that sink in. The takeaway is just profound. The total amount of energy in the entire universe is fixed. It never ever changes. All we ever see in any process imaginable is energy just changing its costume, transforming from one form, like potential, into another, like kinetic.
Let's make this super real. Picture a ball being held at the top of a tall building. Okay? In that one moment, before it's released, all of its mechanical energy is potential energy. It's way up high, but its velocity is zero, so it has no kinetic energy at all.
The second you let that ball go, it starts to fall. As its height gets lower and lower, its potential energy drops. But where does that energy go? It's not disappearing, it's transforming, turning into kinetic energy as the ball picks up more and more speed. One form is becoming the other.
And then, in that split second right before it hits the ground, its height is basically zero. All of that stored potential energy is gone. It has been completely converted into the energy of motion. It's at maximum kinetic energy.
And that is the law in action. At the very top, halfway down, or at the very bottom, if you could pause time and add up the potential and the kinetic energy at any point during that fall, the total amount would always be the exact same number. The energy just changes its form. It's never lost.
So, we've seen that work is really just the transfer of energy, and that energy itself is constantly changing form, but is never ever lost. And that brings us to one last, really fascinating question to think about.
Think about it. Every single time you lift an object, or push a door open, or even just walk across the room, you are acting as an agent of energy transformation. You're taking the stored chemical energy from the food you ate and you're doing work with it, converting it into the kinetic and potential energy of the world around you. Your every single action is a tiny, perfect demonstration of a law that governs the entire cosmos. What you do really matters, because you're a part of that grand, cosmic transfer of energy.